In this session we are going to see what is the exponential form of a complex number and how to operate in polar or exponential form. Remember that to plot complex numbers in an easy way we always have to come here and press enter in these two lines in order to be able to use the complex plot or complex plot bin commands. Now, just a brief summary, the binomial form of a complex number is a plus bi, where a is the real part of the number, b is the imaginary part, and I is the imaginary unit such that I squared is 1. This number can be associated to a point of the plane AB, and we can also describe this point giving the distance to the origin of coordinates, which is the modulus r or its argument theta. So the polar form is modulus sub theta r sub theta. And now we are going to see the third form, which is the exponential form. Okay? In order to do the exponential form, we need to introduce Euler's formula, which tells us that if we have an exponential of a pure imaginary complex number, theta I, without real part, then this is equivalent to say that this is the cosine of theta plus sine of theta I. Okay? Let's check this formula using this exponential. So we have e pi I. Using the formula we get cosine of pi times sine pi I. So if we have a look at number pi, argument pi, the sine, which is the height, is 0 and the cosine is -1, so we get a -1. If we check it with Maple, the exponential of pi I, we get a -1. Okay? Now that we know Euler's formula, we can describe the exponential form. Remember that when we have a number z equal r theta, this is equivalent to saying that this is in binomial form r cosine theta plus r sine theta I. If we take out the r, we reach this expression where now this is the exponential, so we can write it down as r e to the theta I. So this is the exponential form of a complex number. The exponential form of a complex number is r e theta I. Now, it's important to note that the polar and the exponential form provide the same information, and therefore it's just a different way of writing it. Okay? So let's have an example of these numbers. Let's make a plot. So the first number that we have is 1 plus I, 1, 1. This is z1 equal to 1 plus I. In this case, it's very easy to convert it to polar because this distance, the modulus, is square root of 2 and the argument is 45, which is pi over 4. So in exponential form, it's going to be modulus times exponential, and don't forget the I. This is very important. Okay? The second number we are given is directly I, so it's 0, 1. So this is z2, this is 0.01, which is I. So the distance, the modulus is 1, and the argument is 90, so it's pi over 2. So we have that this number in exponential form is e to the power pi over 2i. The third number that we are given is 1 plus the square root of 3i. Let me change colors. So we have 1 plus the square root of 3, more or less something like this. This is our number. So 1 square root of 3i, which is equivalent to 0.1 square root of 3. Now, in order to convert it to polar, we need to compute the modulus, which is 1 square plus the square root of 3 square, which is 2. And the argument, since we are in the first quadrant, is directly given by the arctangent of the imaginary part, square root of 3 divided by 1. And this is going to be, if you look at the table, pi over 3, which is 60 degrees. So in this case, we have that this is 2 pi over 3, and in exponential form, 2 pi over exponential pi over 3i. And the last number, you can see that it's this one here. It's the same number as before. Well, it it was something like this. So we have the same, the number is 1 minus square root of 3. This is why we have just the opposite. So this number has the same modulus as before, you can check it, and the argument, so this and this have opposite signs. So we have the same modulus and an opposite argument, so this is going to be minus pi over 3i. Okay? The important thing, since the polar and exponential form contain the same information, the conversion between exponential and polar is automatic, and the conversion between binomial and exponential is the same as when we convert between polar and binomial. So you can go now and do this exercise from the test. Now, even though we did the other day how to convert from polar to binomial, let's just do 2 or 3 exercises to refresh it. So let's do the first exercise. So we have this number here, and we have to convert it to binomial. You can see that this is the same as 1 e minus 5 pi over 6i. So the modulus is 1 and the argument is minus 5 pi over 6. So remember that in order to convert from polar to binomial, we need this table. So we have this formula: r cosine of minus 5 pi over 6 plus 1 times sinus of minus 5 pi over 6i. If we make a plot, we have minus pi over 2. So our number is in here. So this is going to be minus 5 over 6. So we are on the third quadrant. And remember that we only know the values of the sine and cosine of the first quadrant. So how do we move from the third to the first? We add pi. So what we are going to do is, instead of cosinus of minus 5 pi over 6, we add pi, so we get pi over 6. This is from the third to the first. So we are going to put pi over 6, pi over 6, I. But now, the sine of these two angles, so it's opposite in sign, so we need to put a minus here. And the cosine, this and this, have also different signs, so we need a minus here. If we are on the third quadrant, both A and B are negative, so we need two negatives. So now we go to the table: cosine square root of 3 divided by 2, sine 1/2 over I. So if we do it with Maple, we get the result that we expected. Now, from binomial to polar, we have now two different numbers, and this can be done in this case just by making a plot. So I have these two numbers here. 1 minus 1, this is 1 minus I. Of course, here, okay, we want to convert them to exponential. The first one, we can use the formula 1 squared plus minus 1 squared, but it's going to be square root of 2. And the argument, as we look at the plot, this is minus pi over 4. It's minus 45 degrees. So this can be just because A and B are equal. So Z1 is going to be square root of 2 minus pi over 4, square root of 2 e to the power minus pi over 4i. So this is the first number that we get. You can check it, polar, this is the modulus and the argument that we got. And the second one is minus 5i, is directly this number here, which is equivalent to 0 minus 5. So the distance is going to be 5. Remember that the modulus is always positive, and the argument is going to be minus 90 degrees, minus pi over 2. So Z2 is going to be 5 minus pi over 2, which is going to be e minus pi I. Okay? Now, what about if we have a number, you have here, you can check it, that it's not that easy to convert to polar because the arguments are not as easy. So let's have this number here, minus 3 plus I. This number is equivalent to, if we do it, square root of 3 and 1. So this is our number here. So it's z minus square root of 3 plus I, which is equivalent to number minus square root of 3, 1. So the modulus, we always use the formula minus the square root of 3 squared plus 1 squared, 4 plus 3 plus 1, 4, square root of 4, 2, and the argument. So we are going to use the arctangent of the imaginary part 1 divided by the real part square root of 3. But remember that when we use the arctangent, we only get values in the first and fourth. So this is either Q1 or Q4. In this case, it's going to be the fourth quadrant. So this is the arctangent, the value that we are going to get. But our argument is this one. So how do we move from one to the other? We have to add pi. So in this case, the argument is going to be given by the arctangent plus pi. Now, remember that when we have the arctangent, we can take out the minus, so we get this, and now we go to the table for the famous table. So we look for 1 over square root of 3, so it's pi over 6, so we get minus pi over 6 plus pi, 5 pi over 6. Okay, so our number, which was minus square root of 3 plus I, has a modulus of 2 and an argument of 5 pi over 6, and in exponential form it's going to be 5 pi over 6i. Don't forget to put the I, otherwise it's a real number. And you can check it like here with the convert command, and you get what we have. So now that you know how to the three forms for a complex number and how to convert one from the other, let's go to the operations in polar exponential. So this is an important table. So in binomial form, remember that it's very easy to add and subtract, and we can do product divisions and powers, but sometimes it can be large. So binomial, easy to add and subtract. We can also multiply and divide, but sometimes it's too large. And we cannot do roots. What about exponential? We cannot add. So in exponential, it's very easy to multiply and divide and make powers. Easy to multiply and divide. But we cannot subtract. In this case, we need to convert the numbers to binomial form. So these two are very important. Okay. So addition and subtraction. If we have two numbers expressed in polar and exponential, we don't add the modulus or the arguments. This is wrong. Okay. What we have to do is convert them to binomial and then add. So let's do this exercise. We have two numbers in polar form. Z1 is 2 pi. Z2 is 5 minus pi over 2. So in this case, since the angles, the arguments are very easy, we don't need to use the formula. So Z1 is going to be modulus 2. So imagine that this is a circle of radius 2 and angle pi. So this is our number. This is going to be minus 2. And now we do another circle, this time of radius 5. And we go for minus pi over 2. So this is our number. This is Z2. This is Z1. So this is minus 5i. So Z2 is minus 5i. So we get that Z1 plus Z2, which were given in polar form, which could also be written in exponential form. If we have to add them, we have to convert them to binomial, and in this case we have the addition directly. Okay, so what we have to do is we convert them, okay, either using the formulas that you have here, minus 2 minus 5i, and then we just add them. So to add and subtract, we have to convert them. You can now move to do this exercise. Product and division. In order to do products and divisions, we are going to use these properties here. The first three of them, we already know them from the real numbers. So the first properties is that the same properties that we got for the real numbers, they are also correct when we have complex numbers. So if we have the exponential of two numbers, we can split them between. So we have two numbers on top which are added. We can split them by doing the exponential of the first one times the exponential of the second one. Also, the exponential of 0 is 1. And the exponential of a minus a number is 1 divided the exponential of the number without the minus. Okay, so these three properties we already know them from real numbers, and it's nice that they also hold with complex numbers. This, however, is a specific property of the complex numbers. So what is this property telling us? So imagine that I have a complex number, okay? So z e theta I means 1 e theta I. This means modulus 1. So I take this one here, okay? Modulus 1 argument theta. So this is my number. So this is theta and this is 1. And remember that if I add 2 pi, so you can see that when I add 2 pi to the argument, okay, what I get is the same complex numbers. So what I want is that these two numbers are the same because they represent the same complex number. And the same if I remove one circle rotation, or the same if I add two circle rotations. Okay, so this property, what it's telling us is that this is a complex number of modulus 1 and argument theta. This one is a complex number of modulus 1 and argument theta plus 2 pk. Since these two arguments are the same and these two modulus are the same, these two expressions represent the same complex number. So we want this to be equal, and this holds. So this means that the exponential is well defined, so that since these two complex numbers are the same, the exponential also is the same. Okay. So now that we know this, let's make products. So let's make two exercises. We first start with product of two complex numbers. So we are given this complex number 2 exponential of pi over 3i and z2 3 exponential of pi over 2i. And we want to make the product, so we will proceed as if they were real numbers. So we have this one, we have this one, so now we join the real numbers and we join the two exponentials. So now using property 1 we can join the exponents. So now we can also take common factor, and now in the end we get 5 pi over 6i. So what we have done is, this was a z times z2. So we got that a number with modulus 2 and argument pi over 3, a second number with modulus 3 and argument pi over 2, and the product, we get that we multiply the two modulus and we add the two arguments. So we multiply the modulus and we add the arguments. What about if we divide them? Okay, so imagine that we now have to do z1 over z2. So this is going to be this one here. So again, we break the two of them by splitting the real numbers and the complex one. And now we can use property 3, which tells us that we can move up the one we had on the bottom by just putting a minus. Now we use property 1 to join them, and I do it directly. And now I just have to do the subtraction. So the result that I'm going to get is pi over 3 minus pi over 2 is minus pi over 6i. In this case, when we do the division, you can see that this result is r1 over r2. So we divide the modulus. And the result, the argument, is theta 1 minus theta 2. So we subtract subtract the arguments. Okay, so when we divide, when we multiply the modulus and we add the arguments. When we divide the modulus and we subtract the arguments. And what about the conjugate, the third property? So if we are given a number which is 2 pi over 3i, we can make a plot of this number. It's going to be 2 and pi over 3. I think that is something like this. So this is going to be equivalent to a number a plus bi. Okay, and when we conjugate, we keep the same a and we put minus b. So this is going to be its conjugate. Okay, z1 conjugate, and as you can see, these distances are the same, and the argument is just minus the argument. So if I want to conjugate this, I have to put the same modulus, and I just have to put a minus in front of the argument. Okay, so when we conjugate, we have the same modulus minus the argument. Okay, and this reason is because we have this plot. So in general, when we multiply the modulus, we add the arguments. When we divide the modulus, we subtract the arguments. And when we make the conjugate, we just keep the same modulus and we change the sign of the argument. So now that you know this, you can move to this exercise. And if you have more time, you can do the following exercises here and this other